In this unit, we will see the experimental progress made with the realization and verification of topological insulators. Although topological insulators were first predicted to be realized in graphene, spin orbit there was too weak to create a sizable gap. The first two-dimensional topological insulator, or the quantum spin Hall state, was therefore realized in mercury telluride. This is the theoretical prediction, where you see the band structure of mercury telluride compared to the band structure of cadmium telluride. Cadmium telluride is a trivial, strong insulator, where we see a gap of about 1.5 electron volts. In contrast, mercury telluride is a semi-metal, but as you can see, the order of the gamma 8 and gamma 6 bands have been inverted relative to cadmium telluride. This band inversion signifies the possibility to realize the topological insulator. However, mercury telluride is a semi-metal, not an insulator. Therefore, the theoretical suggestion was to take mercury telluride, to create a thin layer of it and sandwich it between layers of cadmium telluride, and by this get a quantum well in which quantized two-dimensional topological insulator will be realized. This is exactly what was done in this experiment, where you can see the resistance as a function of backgate voltage, and the different plots represent different thicknesses of the material. As the thickness grows, we start to see this plateau forming in the resistance within the semiconducting gap that forms, and it directly signifies the realization of these edge channels, helical edge channels that form on the edges of the mercury telluride quantum well. So this was indeed the first realization of the quantum spin Hall states of a two-dimensional topological insulator. Later, we have observed other suggestions for the realization of quantum wells of two-dimensional topological insulators. For example, the interface between indium arsenide and gallium antimony, which is also suggested to form an inverted interface gap, and indeed quantized conductance was measured, although this interface layer is somewhat debated about its topological properties that could come also from trivial modes that are realized at that interface. So this is one suggestion for the realization of two-dimensional topological insulators through the formation of quantum wells. A different approach is to grow thin layers of materials with strong spin orbit coupling, for example, bismuthine and stannine. So the strong spin orbit coupling variants of graphene in that sense, which are predicted to form two-dimensional topological insulators. And here you see the experimental realization. So a monolayer of bismuthine has been grown in molecular beam epitaxy and subsequently measured in scanning tunneling microscopy, and what you see here is the local density of states as a function of position as we cross two steppages of this bismuthine layer, and what we see is that on these steppages we have an increased local density of states that possibly signify the realization of helical edge modes on these steppages. And very similarly in stannine, the prediction is again to realize two-dimensional topological insulators with helical edge modes, and a monolayer was grown in molecular beam epitaxy and measured in scanning tunneling microscopy, where again we see in the bulk the blue dispersion, and on the edge we see this slightly increased density of states, which in a calculation is predicted to hint on the existence of helical edge modes on the edges of stannine. So by now we have two possibilities to induce two-dimensional topological insulators. Let's see the third one, which is taking transition metal dechalcogenide compounds, van der Waals materials that can be exfoliated into their two-dimensional form, and some of them, like quantity tungsten ditelluride, are predicted to realize two-dimensional topological insulators, where very clearly in calculation we can see the bulk semiconducting gap and the helical edge modes that are supposed to form within this gap. Let's look at the spectroscopic visualization of tungsten ditelluride, where here we see both ARPES and STM measurements of the same sample. So in ARPES we see the semiconducting gap that opens around the Fermi level. Its width is about 40 millielectron volt, and correspondingly in the image local density of states in STM we see this suppressed density of state that goes down to zero density of states, signifying indeed the existence of bulk gap in tungsten ditelluride in the bulk of the flake. Now when we go with scanning tunneling microscopy towards the edges of the flake, this is what we find, an increased density of states at the edges of the flake of tungsten ditelluride that indeed signify the existence of some edge modes, potentially helical edge modes. And when we go to transport experiments on tungsten ditelluride exfoliated to the monolayer limit, we indeed find as a function of backgate that the conductance drops down and forms this plateau, which is independent of gate voltage, and again possibly signifies that the current is now channeled through edge modes in this material. Other compounds have been also suggested and verified to form two-dimensional topological insulators like moly ditelluride and others. So clearly we've seen that two-dimensional topological insulators can be realized in different ways. They do not necessitate the application of magnetic fields, unlike the quantum Hall effect. However, topological insulators also offer us the ability to go to higher dimensions. So let's see how we do that. One way is to take our two-dimensional topological insulators and stack them. However, this recipe would not realize topological insulators, but rather weak topological insulators. One example is bismuthine that we've seen before. This is what happens when we take bismuthine and stack it into the three-dimensional form of bismuth. This is the band structure that we get. One complication is that this band structure has this tiny gap at the L point that we cannot with certainty verify what is its topological origin. Is it inverted or not? And this will affect the whole topological classification of bismuth. It can either be a weak topological insulator, a higher order topological insulator, and indeed this ambiguity exists also in experiment, where some experiments suggest one topological class and others suggest a different one. In order to lift this ambiguity, what we need to do is to open up the L gap, so we can clearly say what is the topological classification, and this was exactly the suggestion made in the LOE bismuth antimony, which is the first realized three-dimensional topological insulator. So as we do bismuth with antimony, what happens to the L gap is that it evolves and grows until we can clearly say that the bismuth antimony should be a topological insulator. Bismuth antimony was realized and measured in ARPES that indeed have seen an odd number of surface bands that cross the Fermi level, 1, 2, 3, 4, and 5. Having an odd number of surface states means that one of them is a Dirac state that is not paired with the counterpart. Having an odd number of surface states means that this material is necessarily a three-dimensional topological insulator, which is indeed the first verification of this compound. Let's look at the scanning tunneling microscopy results, where quasi-particle interference have been measured, and here it is compared to the calculated spinless scattering picture and spin-full picture. What you can see is that the measured scattering pattern is much more similar to the spin-full case, which verifies that not only bismuth antimony is a three-dimensional topological insulator, it also hosts the spin selection rules that prevent backscatterings of electrons and give them the protection from the localization. So this was the first realized topological insulator in 3 dimensions. However, as you can see, it has a rather complicated surface band structure with several surface pockets. So the next step forward was indeed the realization of the canonical 3-dimensional topological insulator, which happens both in bismuth selenide and in bismuth telluride, where first of all, in the calculation, we see a very large bulk gap on the order of 300 millielectron volt, and within it, on the surface, we find a single band, which is the Dirac surface states of this three-dimensional topological insulator. This material was synthesized, measured in ARPES, where clearly you can see the surface dispersing Dirac band, both in bismuth selenide and in bismuth telluride. So here we see also the scanning tunneling microscopy imaging of the surface states in bismuth selenide and bismuth telluride, where we see this very clear standing wave pattern, quasi-particle interference from this steppage. And when we follow its decay, we see that it actually decays quite fast with a high power of 3/2, other than 1/2, which happens in trivial surface states, which means that these surface states are protected from backscattering. They can still be side scattered, but they cannot backscatter, which gives this high power. So again, some verification of the protection from backscattering for these topological surface states. And also in the two-dimensional imaging of the quasi-particle interference, we see that the pattern becomes more and more circular and isotropic as we approach the Dirac node on the surface of bismuth selenide and bismuth telluride. So this was indeed the realization of the canonical topological insulator, bismuth selenide and bismuth telluride, and following that came many other suggestions for the realization of topological insulators in 3 dimensions. For example, the Heusler family of compounds, where what you see here is the size and sign of the bulk gap as a function of the average atomic weight. As the atoms become heavier and heavier, the spin-orbit coupling becomes stronger and stronger, and indeed you see this nice correlation where as the atoms become heavier, the gap first closes and then reopens inverted, meaning that all these compounds in the bottom right corner of the diagram are predicted to be candidates of forming 3-dimensional topological insulators. More recently, we got a more comprehensive tabulation of all possible 3-dimensional topological insulating phase that can be realized in high-quality synthesized compounds, where we now have tens and hundreds of predicted, suggested 3-dimensional topological insulators. Some of them have been also verified in experiment. So we can clearly realize and verify the existence of 3-dimensional topological insulators. The next step is to perturb them, to break the protecting symmetry, which is time reversal symmetry, and see if we can induce a gap at the Dirac point, and by doing so, we will also generate new types of topological states of matter. So the first approach was to take 3-dimensional topological insulators and dope them with magnetic elements. Here is an ARPES measurement of between 12 to 16% manganese doped bismuth selenide, where you can see the formation of this small gap in the surface band structure. However, when we go to scanning tunneling microscopy visualization, we see a more complex picture. We see that actually there's a lot of disorder introduced by the manganese dopants, which makes the whole band structure fluctuate in energy and momentum as we go from point to point on the surface of the material. Still, if we look with higher energy resolution at the evolution of the spectrum across the surface, we can see the formation of a gap around the Dirac point. However, this gap is fluctuating in size and in energy as we go from point to point on the surface. This suggests that potentially we can induce magnetism and gap out the Dirac point by doping topological insulators with magnetic elements, but they also introduce a lot of disorder that can potentially deteriorate the formation of a unified topological phase on the surface of 3-dimensional topological insulator as they become magnetic. A very interesting alternative approach was introduced quite recently, where we realize topological insulators which are intrinsically magnetic. The prime example is manganese bismuth telluride, which is formed by interleaving layers of bismuth telluride, the three-dimensional topological insulator, with layers of manganese telluride, which is a magnetic insulator. Together, they are predicted to form an intrinsically magnetic three-dimensional topological insulator, where interesting phases, magnetic and topological, can occur. First of all, this material is predicted to be an antiferromagnet, which means that its spins are polarized within the layer, however they are antipolarized among the different layers of the material. As a result, if we have an even number of layers, the bottom and top layers will be terminated by spin oriented in opposite direction. This would form an axion insulator. If, however, we happen to cleave the material and get an odd number of layers, then the spins will be oriented in the same direction, giving rise to a Chern insulator. If we now apply an external magnetic field and polarize all the spins to the same direction, forcing it to be a ferromagnet, again we will get a Chern insulator. So let's see what the experiment found. This is ARPE's visualization of the surface states of manganese bismuth telluride, and we get, again, somewhat ambiguous picture. Some of the experiments report the formation of a surface gap at the Dirac point. Other experiments do not see such a gap. So the picture is not yet conclusive, and again, when we look with scanning tunneling microscopy, we see that not all the manganese atoms go into the manganese telluride layer. Some of them still dope the bismuth telluride and substitute bismuth atoms. As a result, we again get this disordered picture in the manganese bismuth telluride surface. However, if we now go to transport measurement, we see promising results where both quantized anomalous Hall conductance was imaged, signifying that a monolayer of manganese bismuth telluride has a Chern number of 1 and does form an anomalous quantum Hall insulator. It has chiral edge modes formed just by the magnetism and spin-orbit coupling of this compound. And if we now exfoliate an odd number of layers, we can indeed visualize the axion insulator, where we have 0 Hall conductance within the bulk semiconducting gap. And if we apply strong enough magnetic field to polarize again all the spins, we end up with a Chern insulator with a finite quantized conductance, Hall conductance, that suggests a Chern number of 1. So indeed, manganese bismuth telluride seems to suggest a promising route for the realization of magnetic three-dimensional topological insulators.